Hi.
Hola, buenas.
Hola.
Hola.
Any questions?
I think I have a question about problem set.
Okay.
But it's like really specific. In problem 1B, we have to adopt a DM of 12,000. Yeah, parsecs per centimeter to the degree. But I think that we might need a centimeter to the -3. So the
Probably, yes, it should be to the -2.
okay, because
It probably was
not,
just a mistake in the.
okay, because if not, I was having a really big problem with the with the unit. Okay,
Yeah.
thanks.
Yeah, it should be density, right? So, okay. Any other thoughts, questions? No. Okay. So let's begin. Okay. So here is a collection of lovely images from Hubble, mostly. What is interesting about them? What do you notice about them? Like they're the most, I mean, you know, they're the striking images that Hubble has been observing for the last 15 years. What are they observing? What are you seeing in these images?
Mass ejections.
So in some cases, yeah, mass ejections, jets. But specifically, these are images, right? What are the images observing physically? Is it continuum? Is it line emission? You don't know.
I don't know. I'm not sure. I would just be guessing.
Yeah, no, so in almost all of these cases, what you're seeing is, you know, they have filters, right? Broadband filters typically, but the emission in those broadband filters is being dominated by one or a few emission lines. And so when they make a color image like this, what they're really doing, this is just an emission line map. And so, and that's why they look so striking, is because you have emission processes which are, you know, being dominated by, say, a shock region, and you're then probing that in the image, right? And so this is a really nice way of just visualizing the different emission regions. And, you know, for instance, here you see this thing has, you know, maybe this is like the edge of a jet or something. And then you have, you know, something else which is going on here, which is an accumulation of mass into a thin shell. But the point here is that most of this emission comes from emission lines. And so we could do the exact same thing in Chandra, and in fact they've done that, and you also get these very impressive sort of images. And the point of it again is that the continuum, right, isn't going to necessarily be tracing super compact regions, or not necessarily super compact, but the continuum emission may not be tracing the same morphology as lines. And so you can use that to kind of understand what's going on here. And so what these images are kind of showing you is just a very simplistic spectrum at each pixel, right? And I mean, again, it could be continuum versus continuum, it could be continuum versus line, it could be line versus line. But if you were to actually extract the spectrum from each of these pixels, right, you would see something like this. And so this is an X-ray image of a supernova remnant, and so you can see iron, calcium, argon, silicon, sulfur, et cetera, right? So the images were kind of taken in these bands and then put together like this. Except for the Crab Nebula, which is actually continuum. I think this is also maybe a cluster, so it's also continuum, but these are supernova remnants here. Likewise, this is a spectrum from the COS instrument on HST. And so you have all of these different emission lines, which you can see are really high, equivalent with lines over the continuum, right? The amount of emission in the line is equivalent to a very broad continuum band. And so they can dominate that. And again, this is just a different object, but again, a spectrum where you have very high equivalent with lines and very low continuum. Or it's not that low, it's normalized flux, but the lines are popping up there. And then these are just some example AGN where you have really broad lines, which again can be a pretty large factor of the total emission from this band. So that's useful, and that's kind of these images are sort of prevalent and burned into people's minds, but one needs to sort of step back and think about what do they actually mean? What do the images mean? What do even the colors mean? And without that information, you don't necessarily know what physics you're talking about. And so that it's sort of critical to understand, okay, the red filter is this particular wavelength, which in the rest frame means I'm capturing oxygen 3, I'm capturing H beta. The blue might be, or the orange, the purple here might be, something at 6,000 angstroms. So I'm capturing H alpha and nitrogen 2 and sulfur 2, something. So just to kind of, you guys should be asking questions about, okay, what am I actually seeing here, right? And trying to pick it apart and say, okay, what is the physics involved that's leading to this? Okay, so that I hope leads into some of the discussion we had about how do we produce emission lines, and then the discussion today, which is how do we actually think about an equilibrium, reaching an equilibrium, or if we have some neutral gas and we have a photon field, what is the probability of the atoms to absorb a photon and release an electron? Or if we have an ionized region, what is the probability, given some density and some photon field, what's the probability that an electron will recombine with its atom, an ion, and emit a photon? So that's where your headspace should be as we discuss this, right? So many of the things that I was showing you before, these images from HST in particular, most of these things are planetary nebula. So they are a not very massive star, a few times the mass of the sun maybe, and at some point in late stage evolution, they had a slow evacuation of the outer layers, and then the inner layers collapse down to form a white dwarf. And so the white dwarf is now ionizing that medium, which is slowly expanding at a few tens of kilometers per second. And so over 50,000 years, 100,000 years, whatever, that will blend into the interstellar medium. And then it will vanish, you'll have a white dwarf, and that'll be that. Right, so it's a very limited evolutionary stage. And similarly with the supernova that are shown in the Chandra ones, these are exploding, and now we're talking about velocities of 10,000 or 5,000 kilometers a second. And so over the course of 10,000 years, they will blend into the ISM and enrich the ISM with metals. So one of them, because these planetary nebulae are so distinct in their spectra, AGN are also distinct in their spectra. They have really strong high equivalent with emission lines. They were the first things that were noticed when people started taking spectra. And in fact, planetary nebulae were noticed in the 1800s. Right? You know, as soon as people started taking photographs of the sky and in different filters, they discovered these things, or dispersing the spectra. So typically the planetary nebulae and AGN in particular have super strong lines of the Balmer series, in fact also the Lyman series and the Brackett series and the Paschen series. But in addition to that, they have ionization lines from oxygen 3, nitrogen 2, sulfur 2. And in particular, this line, oxygen 3 at 5,007 angstrom, was initially referred to as neblulium. I can't pronounce it, but mostly because it was just associated with planetary nebulae in the early days, and so it was something that was only seen there. It wasn't something that was necessarily seen on Earth or anything. So that's kind of the perspective. The way we deal with this is, in these particular types of objects, you have a central ionizing source, which has, it's radiating photons that have high energy. They're UV photons. And so the gas around it is initially cooler and then is photoexcited. So it is receptive to these photons, takes them in, and becomes ionized. And so the gas in at least a photoionization equilibrium, you generally have a central ionizing source, UV strong continuum, and you can then, if you can assume the sort of region has become stable, has become an equilibrium, then you have rate equations which dictate the number of atoms which are ionized versus the number of atoms which are recombining, and you can do a detailed balance. And so that's kind of what's shown in this equation here, which is, so the rate of change of, this is the number density in a given ion state. How that change is dictated by the number in the lower state that are sort of being ionized. And so, they have the lower ionization state, and you have a photon, and you ionize it, it feeds into and creates a new number here. And then you have the number that are leaving that state, either by recombining, going back down to the lower ionization state, or ionizing to a higher state. And then, of course, you have the number that are coming down from the higher state and going into this state. And so this whole sort of detailed balance is how we would be able to understand the physics of these particular nebulae. And so in particular, this nomenclature is a little weird with this lambda, which isn't the photon, it's the ionization rate. When we're talking about going from stage Z to, or basically it's the transition rate. So in this case, it's going from stage Z to Z+1, so high ionization states. There we would use the Saha equation. But then you could also have the transition rate going from the lower state, or sorry, the higher state to the lower state. That's just the recombination rate, right? And so in equilibrium, this change would be 0. You'd have equal numbers of atoms being ionized and equal numbers of atoms recombining. And so in that case, then you have that this ratio is going to be equal to this ratio. And so this simplifies things a little bit. You can, of course, have situations where you're not in ionization equilibrium, right? And so then that's a more complicated process because you're going to have changes over time as the entire physical sort of ionization structure changes. And this could be due to the fact that your central source is varying. You have a variable source, and so obviously that's going to change the, if you have a Strongman sphere, that will change the radius of the Strongman sphere and so forth. So this connects adjacent stages. And so you'd have to do this for each ionization stage, right? So each ionization level. And of course, this then gets complicated when you have to account for going doubly ionized things, so going from the neutral state to a second ionized state. But you can sort of do it. But typically, you only for a given temperature, plasma or whatever, you can typically get away with just doing the 3 ionization states and worrying about that. So the processes that come into play here that dictate the transition rate are photoionization, which is what we're talking about here, but also collisional ionization. So you could have the medium has energetic electrons, and the electrons can compete in this process. You also have radiation recombination, which is sort of the opposite of photoionization. And you also have something called dielectric recombination, which is kind of a type of recombination. And so we're going to go through these in a little bit more detail to sort of demonstrate how we would calculate something related to that. So the first one is sort of the one from the example, which is photoionization.
Hey, Professor?
Yeah.
Oh, sorry for interrupting. I have a question. Hopefully I'm not derailing the topic, but I was wondering, how are the continuum images you show? How are these images generated?
Well, so take this spectrum, right? And so you would say, okay, let's take a continuum image between this, it could be something like actual continuum, so from 0.5 to 2 keV. So it could be all of this, right? And then you could take another one from 2 to 4, and then you could take another one from 4 to 8. And so that would be a true continuum image, right? And that would largely show you the continuum here. You could take smaller images, smaller band images that are just around 2 keV, which show the silicon. And you could compare silicon to sulfur to iron, right?
So is it not a problem that there are lines in the image to take the continuum?
Well, so we should define what you mean by continuum and what you mean by lines, right? And so, yeah, ideally, what you would try and do is isolate the continuum, isolate the lines. And so you would have a line-only image and a continuum-only image, right? That in general is tricky to do, particularly if you only have broadband filters.
Right.
And so you can do it by taking a narrowband filter and a broadband filter, or a couple of broadband filters, to estimate the continuum, and then normalizing and subtracting it off. But in a lot of cases, the continuum might be dominated by a strong high equivalent width emission line. And so you can just take an image of the continuum, and you're going to have a strong contribution from the line. And then the continuum might have some other features in it, but it might not matter. And so that's kind of what's shown here, is that there is a strong contribution from the emission lines in these continuum images.
Okay, I see.
Right, and mentally you have to blend that information, right? So if you like drilled in and took each pixel and had a spectrum of it and then looked at it, right? Like you could with an IFU, then it's much easier to kind of pick apart what's going on. The problem with these is that you have a mix of information. And so it becomes a little bit difficult, you know, they're striking images, but it becomes a little bit difficult to know what is continuum and what is emission line.
Okay.
Yeah.
Thank you.
Okay. So skipping forward again. So we have photoionization. And so photoionization is known as bound free, right? So you have a photon coming in and an electron in some shell at some level will intercept that electron, or so that photon energy, and that energy is then imparted into the electron. Right? This is simply the photoelectric effect. Right? So you need at least the photon, it has to be at least have enough energy to liberate the electron. Otherwise it will just jump up a level. It won't actually leave. Right? So it at least needs, this energy at least needs to be the ionization potential of that particular energy level of the electron. Right? So this photon has to be greater than the ionization energy. And then if it has any more energy, that energy will go into the kinetic energy of the electron. So you have some electron, it pops off and it has some kinetic energy, right? So it's 1/2 mv squared. So that's pretty simple to sort of understand. The photoionization rate, which is given by this, so from stage Z to stage Z plus 1, a different nomenclature would look like this. So capital gamma, Z to Z and Z here, whereas big Z is now the atom atomic number, right? So this is the number of photoionizations of some element Z per unit time in this given stage. And so we can think about this as there's a cross-section as a function of frequency for this electron to intercept this photon. And then, you know, we would integrate over all frequencies. And then this thing here is the number of photons passing through some interval here. So this is just this is the photon flux. This is the actual photon energy, right? So this is the number, just the number of photons times the cross section integrating over the frequency. That's all it is. So if you don't have many photons, right, then your rate of photoionization is going to be lower. Just makes sense. And then you have this thing, which depends on the atomic structure. And we'll go through that in great detail in a second. So just to note some nomenclature here. So whoops. Typically you have oxygen 1 would be neutral. Oxygen 2 is singly ionized. Oxygen 3 would be doubly ionized. Right, so oxygen has 8 electrons. So doubly ionized, you lose the last 2 electrons, or 2 electrons in general. Right? It can be kind of anywhere in the structure. Okay, so how do we calculate this thing? So the behavior of this cross-section, the bound-free cross-section, could either be done using sort of semi-classical approximations, and you can get a rough estimate of that. And so this is kind of similar to how we calculated the line emissivity. And so for hydrogen, this is relatively straightforward. So we can think about the absorption for the nth level can be given by this value here. And so this cross-section goes as the frequency, 1 over the frequency cubed. And it also has a term, it goes as the n level to the 5th power here. And you also, interestingly enough, have this thing here, which is a Gaunt factor. But it's a Gaunt factor for a specific level and a specific frequency. And so it's a fudge factor, right? And so you can go in the laboratory and you can measure these. And this is actually pretty much how we know these things, is because people go in the laboratory, they irradiate an atom with a bunch of different photons in different sort of configurations and tabulate it. Right? So they tabulate this, and then they can tabulate this cross section. And so there are sort of functional formula for most of the elements and ions that we would care about in terms of being astrophysically interesting. And so an example of this is published by Werner and Yakovlev. And so you can go and look up those functional formulae. You can also look up detailed computations, which are done by the opacity project. This is known as TOP. There's also an iron opacity project. So the original opacity project is published as Seaton et al., and the iron one specifically, because iron is such a complex atom with, I guess, 26 different electrons. This is one of the published, it is published by Butler, but there's several here. So you can go and actually look at the iron project or the top base, and it's kind of, when you go here, it's very complicated about what you actually need to look up, but you can look up very specific things about this, a particular level of a particular atom. So these are just some examples from Werner showing the functional forms. So this is a function of EV. So this is the photon energy, and then this is the cross section, and it's in units of megabarn. And it's a weird unit, but that's what it is. So the barn actually comes from, there's a colloquial saying, which it's, so big that you can hit a barn. Like if you throw something against a barn, it's very easy to hit. So these are in megabarns, whatever that unit is. So the point here is that you see that there is some structure to it. So the 1s is actually pretty simple, right? So you have above some energy, you can then pop the electron out of its orbit, its orbital, and then the cross section is very high for low energy photons. And as the photon goes up, this actually goes down, right? Which is this functional form here. So as the energy goes up, the frequency is going up, and so the cross section goes down dramatically. So this is just this 1 over nu cubed, or 1 over energy cubed. Similarly for the 3s state, it's pretty easy to calculate. When you go to the p or the d states, you can see that there is now extra complexity here. And this is for iron in particular, a subshell of iron. And so you now have to deal with cross sections which don't necessarily go like this, but they have a flatter portion, or maybe actually they peak at higher energies rather than at the exact energy where you would be able to the ionization potential. So these are nice, and you can use these. How well do they actually compare to reality is a different question. And so this is a cross-section from the top database, which is from the laboratory. And so they've irradiated this F3, the doubly ionized iron. And you can see that now you have a flat sort of section here, and then you have a fall off, which is related to the ionization potential. But then actually there's some possibility of being able to ionize it even for photons which are a little bit less. And this is due to the fact that this is a very complex atom. And so you can ionize some of the internal structure, and that allows the atom to, or the electron to be popped off, but there's some extra stuff that goes on in the atom. So the atom might be not necessarily in its ground state, and so a photon that comes in with a little bit less energy, plus the energy that's already in the atom, allows that electron to pop off. And so there's some resonances here, which are kind of noted by this. But the cross-section is still, it's hugely diminished, but it's still, there is a possibility. You also see little gaps here, and these are related to different orbitals, and there might be a higher probability for a photon of exact energy, which can benefit from resonances in the orbital structure. So one of the other things that, and this is kind of related, these edges here, these blips here, this is related to the fact that you have what's called autoionization resonances. And so you can imagine here that you have two electrons which are in higher orbitals, and so they have, this is not the ground state, and so maybe you ionized this thing here, and so at some point what could happen is that this could drop down, and then this one, because you have some energy that you're giving away, you could give that energy to this electron and pop it off. And so in this case, there's no photon being emitted, right? It's just, you had something that happened beforehand that left you in this state, and then the atom relaxed and shed an electron, it ionized, but due to sort of what's called an internal photoionization or an autoionization resonance. And this is known as the Auger effect. Okay, so if you look at some sort of material is in the interstellar medium of, let's say ISM abundance, it's sort of a typical Milky Way abundance. So you have a bunch of different elements that are there, but they're in trace form, right? So the majority, you have hydrogen, you have a little bit, 10, 15% helium, and then you might have trace elements of the higher things. So what's sort of interesting is that this cross-section per hydrogen atom, actually this is a material of solar composition, not ISM composition, but nonetheless, the point is still sort of the same, is that you have, so here's the cross-section for the electron, and then here's the cross-section for iron. And then this is the total cross-section if you sum up all of the material. And so you can see that at very high energies, iron effectively dominates the total cross-section, right? Up until a point where the electron has a higher cross-section at very high energies. And so if you normalize this by e to the third power, right, because of this dependence here, right? So if you normalize by that, then you can see most of these transitions. This is the e to the -3 here. So you can see that these transitions come from different elements. And so this cross-section in terms of the energy cubed, you have hydrogen here, you have molecular hydrogen here, which has a relatively small cross-section. Then you have helium, which contributes decently, then carbon, then nitrogen. Then you have a huge jump for oxygen. You have the iron L shell, so this is the second shell. Then you have neon, magnesium, aluminum, etc. And then iron, this is the K shell here, has a huge cross-section. And so this is again what is sort of shown here, where this jump comes in. This is an EV, this is an KEV. And so what's interesting is that in the X-rays, the absorption doesn't come from hydrogen, right? This cross-section is predominantly from these elements here, and not from hydrogen, which has a very low overall cross-section. And effectively, it's just this. So this is interesting because generally you will measure the ISM based on its hydrogen column. So you quote the ISM as having a column density of neutral hydrogen. But actually what you care about is the abundance ratio of this neutral hydrogen, because that's what gives you the absorption, at least in the X-rays. Okay, so any questions about this? No? Okay. So in addition to photoionization, you have the other possibility is to have collision ionization. And so instead of a photon coming in here, you have an electron. and the electron has enough energy that it, through a collision, it pops this electron off. And again, this electron needs to have enough energy to give energy above the ionization potential, and then some. And so the reaction here is you have some atom atomic number and some ionization state, and you have a free electron, and you ionize it, and you have 2 free electrons. And so the collision rate clearly is going to depend on the number density of free electrons and their velocity distribution, right? So number density of electrons, and then this thing here, which is related to integrating over the cross-section and the velocity distribution. Oops. And so we can consider this sort of to be the average velocity times the cross-section. And this is known as the collisional ionization. So again, you can calculate this in the lab, or you have tabulated formulas. So there's approximate formula for the collision ionization rate goes as this sort of function here. So you have some normalization. It's based on the temperature, the square root of the temperature or the velocity, and then it has an exponential related to the ionization potential divided by the temperature, and then this extra sort of functional form, which has some of the atomic physics in it. And so you can look up these, the values here for these things. And typically you can compare this functional form to the actual data, right, that you measured in the lab. And so this is the cross-section for neon, ionized neon, for instance, right? So you can see that it has a pretty slow rise, but it's very distinct from photoionization. And then here's another one for argon 4, so 4 ionized argon. And so you can see the data from the lab smooth over this transition, right? But the formula suggests that there should be some edges to this due to the different levels. And in fact, some of this data doesn't even necessarily agree, which is also interesting. And so understanding sort of why that is. Then this is again argon 2, and so you can see it has a shape that's similar to this. And so again, you can look all of these things up and look up tables. And these are sort of verified by lab results. So that's ionization. The other side of this is, of course, recombination. And so the sort of radiative recombination, which is also known as free bound process. You have an electron which is captured, and in this capture, it might be captured to a high level, and then internally, this will drop down and emit photons. And so you get captured into an excited state, and then you might release several photons in this process. You could also capture it directly and just release 1 photon, right? And so it just depends. This number of photon depends on exactly what happens here. And so this recombination rate is given by the number of electrons, right? It depends strictly on the velocity of the electrons, whether they're going to be receptive to this, and then the cross-section for free bound. And so again, this recombination rate is going to be the number density of electrons and the average of the velocity and the cross-section. And again, you can use the recombination cross-sections, and these can actually be calculated to some extent from the photoabsorption cross-section. So you can invert this, the bound-free cross-section, relating it using something called the Milne relation. So here's the cross-sections that we showed before, and the free bound cross-section will be related to this, but you have some extra terms here. And the extra terms are related to the frequency, the velocity distribution of the electrons, and then we have our statistical weights. And so the recombination of iron 26 to iron 25 has a cross section which goes like this, and you can see that there are all these resonances, which are due to the LL resonances. So in between the L and the L shell, this is between the L and the M shell, this is between the L and the N shell, and so forth. Right, so you have some higher cross sections that allow you to have double photons come in and be able to emit. So again, coming back to, you'll receive it up here and you'll emit several photons. Okay, there's an alternative recombination which exists in some particular physical scenarios, which is called dielectric recombination. There's actually a third process, which I didn't even talk about here, which is three-body recombination, which is pretty rare. So there you have the ion and you have two electrons, and the combination of those things, typically you have to have pretty high densities and low energies. There you can have where you will be able to recombine two electrons at the same time and then emit some range of photons. But anyway, as I said, that's pretty uncommon. This dielectric recombination is fairly common for astrophysical situations. And so what you have here is kind of like a delayed response. So the electron pops in, and in doing that, there's some energy involved here. That energy goes to exciting an internal electron, which will then later decay. So the initial capture is radiationless, right? And you then end up with an atom which has a non-ground state, or has some extra energy that it's holding, and you have to wait for the decay rate for that particular transition to occur, which might be seconds, it might be hours, whatever. And so that you could then get a cascade. So you could get a single transition back, which would release a photon, or you could end up getting a cascade of photons like we had here. Or you could have an auger-like effect ejection, so you could actually eject an electron later on too. So this type of recombination leads to something called satellite lines, and these are important in certain physical situations. One example is the solar corona, and so you can use these lines to estimate interesting properties about the density and temperature. Okay, so that should account for most of the things that we would have to deal with in our rate equations to look at a detailed balance. And so just to sort of think about this in a very simplistic case, let's assume that we have a cloud of gas. It's irradiated by photons, and we only have one source of ionization, photoionization. And so we assume equilibrium, and so the number of ionizations equals the number of recombinations, and so our rate of bound free, which is going to be our photoionization, is going to be equal to our rate of recombination, right? And so we just have to solve this. And so we have some photon field, and we want to integrate over all the frequencies that are relevant to potentially ionize that particular transition or that particular level or electron. And then we want to compare that to the reionization rate, which is going to be dictated by the temperature of the system, right? The speeds of the electrons and the number of electrons and the number of ions. So you go through and you say, okay, well, this thing is proportional to e to the -3. If we're talking about something simple like hydrogen, we have our recombination coefficient, we have our particle density, and we have our photon field. And a photon field we could relate to our luminosity, right? If we knew the distance. So this thing will end up being a very fast function of the energy. So typically the recombination rate will go as e to the -5 or so. And so this rate here will be proportional to this thing, which goes at e to the -3, this thing, which goes at e to the -5. So this is roughly 1 over e squared. And then you have the photons. So this is the photon flux, and then just the energy of the photon. And so again, this is a quickly declining process with the energy of the plasma. So typically the ionization equilibrium will then depend on something called the ionization parameter. And there are many definitions of this. And so this particular one is the number of ionizing photons per cubic centimeter divided by the number of electrons per cubic centimeter. Right? So this is the number of possible photons, and this is the number of possible electrons to recombine with. Right? Makes some sense. And so again, this is just the flux, right? Or this is luminosity times the energy, and then this is the number of electrons. And so often you will see things quoted in terms of this ionization parameter. Any questions?
I have a question regarding to the dependence of the, for example, in this case, the recombination coefficients instead of the energy. It's like a curious question, but I don't know how this dependence is found, because in the previous slide, there is a dependence to the energy to the -3, but here is energy to the -5. So I was curious about that. If
let's see, so yeah, so our recombination rate here, it's, let's see, this guy, and yeah, so we have, this goes as energy to the -2, but then we have the bound free, and that goes as energy -3, right? So -3, -2, -5.
okay. Thank you.
The trick is bound free and free bound. That's the trick. Okay. So you can, for simple situations, you can do this. And, as I mentioned, for hydrogen, easy. For hydrogen helium, it actually already starts to get a little bit tricky. And so this is just an example of the fractional ionization. So it's a strong Lorentz sphere for the most part, where R1 is the radius of the strong Lorentz sphere. But you can see that at a given temperature, right, it is not a clean bound here. And so, say for a star that has a temperature of 30,000 Kelvin, the fractional sort of range where you have partial ionization is actually quite large now, but partially because you have helium, which is playing a part in this, and so the ionization of helium is down here, but you end up sort of absorbing some of the photons way in here, and so they're not able to contribute all the way out here. And so you have to worry about, you kind of eventually you sort of have multiple spheres for different atoms. And so once you crank this up to 40,000, then you can see that the helium will ionize out, and you'll have something which is actually pretty close to the sort of nominal strong sphere then. And so it's a very tricky problem to deal with. Particularly now, if you add in other elements, then this becomes quite complex in terms of the ionization structure, right? And so you have to give it a lot of thought. And this can then, of course, go back to thinking about some of the images that we saw here, right? And so this is your central ionization source, and these emission lines might be from oxygen and maybe from nitrogen, sulfur. And so you have to kind of think about, okay, what's the density structure here? And then what's the ionization structure going to look like? And that's kind of why you have a density structure which might be bimodal, and then within that you might have some extra properties which are leading to these very interesting forms of or shapes of emission. So go back here. Okay, so in essence, you can do this for simplistic scenarios, but in kind of real situations, this is also pure photoionization or recombination. In most physical situations, you have a combination. So the ionization might be from photoionization plus synclitional ionization plus Auger ionization. The recombination would include both radiation recombination and dielectric, and maybe even three-body. And then you can factor in continuum processes, right, which are going to take away energy from the electrons. So you might have Bremsstrahlung, which will take away energy from the electrons and lead to a photon field. You might have Compton scattering, which has some exchange of electron energy and photon energy. You have dust, which might absorb stuff. So it gets complicated very quickly. And so typically to do this radiation transfer requires complex codes that can kind of handle. And even then, these complex codes will only deal with simplistic versions of this, where you have to make some approximations and say, okay, we're dominated in this regime, so we can only focus on these, two sets or three sets of things. But things like cloudy, there's another program called XStar. There's another program called Dusty, which does the radiation transfer with dust. These try to incorporate a lot of the different transitions and factoring in, the sort of functional forms of the cross sections for recombination, for photoionization, bound free, and so forth. So it's a non-trivial process. Okay, so that in a nutshell is what this class is all about, right? Is sort of combining everything. And so one other thing to kind of consider here, right? That this talks about absorption and emission, and I kind of factored in scattering here a little bit, but it would be useful to maybe review in a little bit broader sense, scattering versus absorption, because the two processes are kind of competing and contributing to one another. And so this is kind of a recap of the last 3 months, right? So we have scattering, which you take photon and matter, and you also you end up with photon and matter, but in maybe a slightly different configuration. It's changed the angle, it's changed the energy, something has happened. And then you have absorption, right? Which is photon plus matter equals matter. And in fact, actually, you also have emission here, which is just matter equals photon plus matter. So scattering can give rise to a number of interesting astrophysical phenomena. So we have reflection nebulae, we have light echoes, polarization, lamina forest in quasar spectra. These are all cases where we have scattering. And the last one you might think is more associated with absorption, right? But in fact, there's resonant scattering around the emission line, around the sort of line resonance, which we need to sort of factor in. And so the cross-section for scattering, right, has some effective area, and this is going to describe how the photon looks or sees the target. And then we also have some cross-section for absorption. And so we might have competing probabilities of the photon being absorbed or being scattered. And so typically this is again why we need something very complex to kind of deal with all of this. We can split the scattering into elastic or coherent scattering and inelastic or incoherent scattering. And these, of course, change as a function of the photon energy. So we talked about, the elastic scattering. We had a Thomson scattering regime, right? We had a resonant scattering regime where you have a photon coming in, and depending on the atom, you might ionize the atom for a second, and then it will recombine and emit the same photon, or roughly the same photon, in a different direction. And then you have Rayleigh scattering, which again, is scattering off of atoms as opposed to electrons. And so we had dealt with this in a way when we were talking about the oscillator. Right? And we looked at how the functional behavior of an oscillator behaved in certain regimes when you had an incoming photon. So we also have inelastic scattering, and this might be Compton scattering. And so you have incoming photon and electron, and you leave with a different one. Another version of inelastic scattering, which again has ionization in its place, is fluorescence. And so you have a photon coming into an atom, and you ionize the atom or doubly ionize the atom. And so then this leads to a initial photon being emitted, and you still have an atom in a non-ground state. And so then eventually this will decay into the ground state, and you will, or sort of a less ionized state, and you will have a second photon that comes out. So you have sort of a cascade of photons. This is slightly different from radiation recombination, but it kind of is similar in the same sense. I'll show you that at the end. And so here, these are basically, this plus is indicating just a higher excited state more than anything else. So these are still bound. This isn't ionized. This is just you have sort of the electrons are in a very excited state, and then when one of the electron decays, you get a photon, and then sometime later you get a second decay and you get a second photon. Okay, so the Thomson scattering, we talked about this before, and of course you get a polarization that occurred from this, right? And that can of course be useful. And this is generally for free electrons. We talked about Compton scattering, and this is an inelastic scattering. And so there we impart some energy. And so we are in the Thomson scattering regime. And then as you get to higher energy photons, then you potentially can give some of that energy to the electron. And that cross-section will go down as a function of the photon energy. Then we also had the opposite process, which is the electron could give some energy to the photon. And we had some relation relating the electron temperature to how much energy it can give. And so we have certain regimes where we have the Compton effect, no exchange, or inverse Compton effect. And so then we talked a little bit about resonance scattering. And resonance scattering took on the functional form, which looked like this, right? So we had that the scattering had a peak, which would occur near the resonant frequency, which is associated with the orbital of the electron. And so if the frequency is much higher than this, then in general, the photon sees the electron as if it were just a free electron. And so in that regime, it just acts as Thomson scattering. Then if the photon is right around the orbital frequency, then you end up getting something which looks like this. And remember, this is the cross-section line profile, right? And so we have there's this natural width of the line that occurs. And so, then it depends also on how close the frequency is to the actual resonant or sort of line frequency. And so typically this sort of process of resonant scattering, generally here you have a huge cross-section. It's boosted with respect to the Thomson cross-section. So this is the Thomson cross-section, and so this thing can be really high compared to this. And so generally, resonant scattering here, it requires a spontaneous de-excitation to occur before collisional excitation or de-excitation ends up occurring. If you absorb the photon, and so the electron is in a higher energetic state, then through a collision, you give that energy away to another atom or another electron, then you no longer are able to emit that photon back out, right? And so depending on the density of the electrons, in particular, because the electrons are what actually does most of the interaction of exchanging energy. So depending on the electron density, if it's very, very high, you'll get a collisional de-excitation. And so typically this resonant scattering requires relatively low densities in order to not be able to collisionally de-excite the absorption. And then finally, we have the regime where the frequency is much less than this, and then we have that the cross-section is proportional to the frequency to the fourth power, which again can be a very high value, right? And this is Rayleigh scattering. And of course, Rayleigh scattering is what we see. That's why the sky is blue. And so Rayleigh scattering, has basically the cross-scattering is a very strong function of wavelength or frequency. And so again, this is our view of the Earth and why you get Rayleigh scattering, or why you get red sunsets. So in essence, all of these regimes are related by the oscillator strength. And so we can think about each transition has an oscillator strength associated with it, which is Fi to J. And so this thing is a dimensionless quantity, but it takes into account the quantum mechanical, the quantum mechanical fudge factor, right? And so we can think about this thing as being proportional to the incidence of these photons resulting in electronic transition is all. So it's just a probability. So if we look at these particular things in terms of the sort of quantum mechanical versions of them, then we have our classical Thompson scattering. We don't have the fudge factor, right? Then for resonant scattering, we have that this cross-section depends on this oscillator frequency and the line profile. And then in the Rayleigh scattering regime, we have that this cross-section is now proportional to frequency squared, but we now have this extra fudge factor here, which depends on the atomic physics. And so this modifies this just like, and so if you were to look at this in sort of a physical terms, this is not to scale at all. But the point here is that frequency increases in this direction, and so is that right? This is here. Yeah. So at high frequencies, you have Thompson scattering. So this is the Thompson regime. Then you might have resonant scattering, which occurs at very specific wavelengths, and then at very low frequencies, you enter the Rayleigh regime. And so this sort of situation is actually embodied in something like this. So this is a Lyman alpha 4 spectrum of a high redshift quasar. And what you're seeing here is this absorption, right? You have photons which are traveling through space. So initially they were at a higher energy than Lyman alpha. And as they travel through space, they get redshifted down towards Lyman alpha. And so as a function of redshift, each portion of the spectrum will, at some distance away from us, encounter the resonant transition of Lyman alpha and have the potential to be absorbed and then re-emitted in a different direction. And so all of the chunks of flux that are being taken out of here are this resonant scattering, right, where they're being absorbed and re-emitted in a different direction. And so that's what you see here. So the final thing I wanted to mention was fluorescence. And so fluorescence is kind of an interesting beast. It's inelastic in that it's incoherent, meaning you have a photon which excites an electron, and it excites an electron by at least 2 energy states. And in doing this, then what happens is that you spontaneously get a de-excitation to an intermediate state. So you emit one photon, but the atom is not in its lowest energy state still. And so depending on how fast this occurs, you might get secondary photons, which come sometime later. And so, or you can actually get a cascade of photons. And so this is an example here where you have a photon comes in, it pops this electron up to this level here. And then what happens is you get a cascade of photons which come down here. And these are the sort of what's called vibrational relaxation. And then you are still sitting in the lowest energy level of say, n=2. And at some point, you will drop back down to the n=1 level, but potentially in different orbitals of that level. Or maybe this isn't n=1, this is n=2, this is n=3, so forth. So this process is called fluorescence. And so, the consequence of this is that this photon is scattered, and then so it's absorbed and re-emitted, but it also changes energy. So it's similar to resonant scattering in a way, right? Where it's absorbing and emitting in a different direction, but in addition to that, you're changing the energy. And so this fluorescence is collectively. You can think about this process. It can also be denoted as Compton reflection. And actually, it's the principle behind fluorescent lights. And this is just showing you an example of, we see fluorescence a lot in X-ray band. And so you have an input spectrum, which might be a power law, and it encounters some material, which is complex. It's not just, it was some part of the ISM. And so it has some hydrogen, some helium, some iron, some nickel, some sulfur, or whatever. And so what happens is you have a high energy photon, which pops, excites this electron into a higher state. And then you get a cascade of photons. And so you'll get these lower energy photons will all be, down here. And then this final photon here will be this one, which you'll see in the X-rays. And so you take an initial spectrum, and all of this energy is absorbed by the different fluorescence of these different lines, right, of these different atoms. And so then these are all fluorescent lines going from this particular transition to this one of the different atoms. And so something related to fluorescence is phosphorescence. And so here what happens is that you excite it, but then you end up moving into a sort of intersystem crossing here, which is a little bit more complex. And there, then what happens is that this time of sort of this cascade actually will be delayed by some amount of time. So basically the re-emission of the photons is not so much instantaneous, but delayed. And so this leads to this phosphorescence. Okay, so I think that covers almost everything possible, all of the different various situations we could have. Are there any questions about this? Any doubts? Obviously, it's a complex process, and so usually you kind of deal with it piecewise, and then you can kind of put together some simplified versions of physical, sort of situations.
I have a technical question related that in order to understand a little better how to apply this. In the past, I have the opportunity to work with Cloudy, and I remember that they uses, well, in some cases when they use Cloudy in Python, they use some values for the coefficients and from the parameters that was like calibrated from data. And according to the paper or the sample of data, the parameters change a little bit the value. And I was wondering if, well, in that time, I didn't understand very well why we can use different values, but now I can see that some of these values are defined in terms of constants and can be like find mathematically in an exact value of. So I don't know if it's possible to use if we are always attached to use empirical values or of observed values from that coefficients and parameters, or we can find specifically in detail these values.
Yeah, so yeah, I'm not sure exactly how to answer your question. I think what you were saying is, okay, we used a value from one paper and then they said we should revise it. And either that was revising it for a different physical situation or revising it because if you come back here, let's see, right, like it may be that the cross sections actually changed with the newer laboratory results. And so they modified the value a little bit to account for the laboratory results. However, the laboratory results, need to be taken with some understanding of what conditions were done to, to understand this. And also like this was done in isolation, right? So maybe there are some, if you have a multi-abundant plasma or gas, the photon fields, there may be some photons here, right, which are more likely to be absorbed by another atom than by this atom. And so you have to compare them. And so it may have been that, they fudged those values to kind of account for that. I don't know. Like, for instance, you could have different abundances in the gas, and that may make a difference to how you might relate one atom cross section to another. I'm not sure that explained anything, but
I think that understand a little bit better.
yeah. I mean, without knowing the exact, without actually reading what you're talking about, it's hard to know why the value changed.
So in that sense, there is not like an agreement between everybody in order to how a specific value we can use, but like every authors have the choice or the possibility to choose a specific value or something, maybe perform some estimation from the codes.
Right. So typically, like you'll see a lot of places will quote Werner, this paper, Werner and Yaklov, and this is fitting formula, right? So it doesn't necessarily take into account the more robust actual laboratory results. And so again, right, like these are functional forms, they're nice and smooth. And then you actually look at this and you have resonances. And so it may have been that Cloudy, so Gary Furland might have said, well, let's smooth this and change the cross section very slightly to account for that, right? So modifying this very slightly to kind of account in a broad sense for these resonances. So I just don't know. I have to go and actually look at the details of what they did and why. That's all.
Thank you.
But yeah, I mean, so very often you will see papers which will say, okay, we took cross sections from this database, we took other abundances from this sort of calculation, and mix those two things, and you could easily take a different set of cross sections and a different set of abundances, and that are also justifiable, and get something which might be very different. And that, of course, is a problem, right? So If you wanted to be super careful, you would have to spend years doing all the things under, various abundance estimates, various versions of the cross section to make sure that things were robust. And even still, you might not know, because someone could come around and say, "Oh, we did a new version of this under better conditions, and we found that this cross section changed by a factor of 2." And maybe that's important, maybe it isn't, depending on the physical situation.
It makes sense. Thank you.
Yeah. Atomic physics is interesting and complex. Okay, other questions?
Yes. The combination refers to, I don't know, to that relic time when electrons and protons were just plasma and were not bound to the hydrogen atom yet.
Correct. Yeah. So you have ions, and they're receptive to electrons, which are floating around. Right. And this is clearly going to be a function of density, because the electron has to find the atom, right, or the ion, rather, or vice versa. Mostly the ions are mostly stationary, right? So the electrons are the ones moving around. So it's mostly the electron has to find the atom to the ion to recombine.
Okay, thank you.
Other questions? Things are clear, things are unclear.
I have a question. In the case of band free, can the electron emit radiation like in free emission?
Well, so yeah, I mean, once it's free, yeah,
Aye.
it's a free electron. It can do whatever it wants.
Okay.
Yeah, and so this is part of the point of this slide, right? Is that once you ionize, then you have to account for the energy losses from this, and to some extent the energy can go into dust absorption as well, which we haven't talked about yet. But it's like a more complex form of this, because it's a complex molecule.
Thank you.
But at least at this point, you almost have all the tools you need to realize that it's a really complex problem more than anything else. But you in simple situations where one or two things dominate, and you fortunately there are astrophysical situations where you can apply approximations and get out reasonable results. And so that's not too bad. But you kind of have to realize what those are, and sort of say, okay, well, in this physical situation, photoionization dominates over collision ionization because the densities are very low, right? And so you could compare the cross sections for a given density and say, okay, this thing dominates. Anything else? No? Okay. So next time we're actually going to talk about some of the physics you can do with emission lines. So these are the scenarios where one of these things dominates, fortunately, for the most part. Okay. So with that, I will leave you guys. Have a good week. The homework's due on Friday at midnight. Office hours should be at 12, I think. Unless, let's see, the golden week is, the golden seminar is at 11. So maybe, yeah, I haven't decided. I guess maybe it might be a few minutes later or whatever, but it should be 12 to 1. So, okay. Okay. Take care, everyone.
Bye.
Bye.